Okay. A few technical difficulties this morning. This little thing I scribble on isn't working for some reason. That's all right. The presentation I'm going to show you actually doesn't have too many things in terms of notes, so we'll be okay here. Other thing in terms of, for those of you monitoring online, the upload of videos of this class. So I still haven't figured that out yet. So I've been trying to use Adobe Premiere, which is supposed to be professional software, and every time I do it, I get 47 gigabyte files when I try and use any type of editing, which I'm sure you don't want to download that. So right now, the ones that are on YouTube right now are unedited videos. So it's all the dead air time and before the class, all that other stuff. Sorry, it's just a little bit of that until I figure out how to edit video properly with professional software. But that's all up there. Everything we've gone through so far is now on YouTube. Okay, so we finished Thursday's class going through this journal article, The Theory of Moving Sources of Heat and its Application to Metal Treatments. And I didn't have time to go through any type of discussion today, or on Thursday, so I wanted to go through a little bit today. And kind of, I'll start kind of discussion, and then we can go where the discussion leads us here. The main message is, this is a paper that I was looking at the problem of arc, and they were trying to derive some simple relationships to try to get the temperature in arc welding. And I think the most interesting plot here was actually these plots right here. This is looking at basically the temperature profiles for welding. One, this is at a constant current for these two, but then you increase the welding speed, and we talked about why the shape changes here in terms of the heat does not diffuse as far forward when you go faster, and we're going to talk about later how this is important for additive manufacturing. This is the case where you increase the current, and so therefore you see that increase the current, and you have basically the temperature, you have a hotter source, therefore the higher temperature spread farther. And this is the case of if you increase the conductivity. So if you were the material you're welding, how far will this temperature spread? And so these are the basic relationships that this paper started to go through. The assumptions on this for this were pretty basic. And so in terms of the discussion, I thought we would talk about what are we missing here when we have types of assumptions here. So they were saying that there's no heat loss to the surface, so that means that Newman boundary condition on both the top and bottom surface. Basically infinite sheets in the zeta and y direction, and finite thickness in the z. But I think there are also a lot of other assumptions that that would happen in this process that maybe they're omitting. And I thought maybe it'd be good to discuss some of these and how that could affect temperature profiles. So what do you think they're omitting here? Basically a purely conduction model and infinite planes. Any thoughts on that?
So can you repeat the question? I apologize.
Sure. So these are the assumptions, the basic assumptions they were using for this arc welding process, where they're trying to understand what is the temperature profile. And the question is, what do you think that they're omitting, and what do you think those emissions would be?
They're emitting convection into the environment. Is that a big deal? I'm not sure about welding, like regular welding.
Yeah, I guess we'll start about maybe what they are omitting, and whether or not it's a big deal. We can get to that in a second. And we haven't really in this class, we haven't really armed you with enough knowledge to say, is that important yet or not? We'll get actually into that in module 4. But in terms of things that are emitting, yes, they're definitely emitting convection. Just a quick show of hands. Who here has taken a heat transfer class in undergrad? Okay, so the majority, but the 2 students have not taken a class in heat transfer before. Okay. So one thing they're definitely emitting is convection into the environment. Okay, so is that going to be a heat loss convection to the environment or a heat gain? Right?
That would be a net heat loss.
That heat. Convection is basically the spread of heat through some sort of medium flowing past the surface, and that essentially, for lack of a better word, convects that resident heat to a different location in space. All right, so if we had convection, if convection was, we would expect every temperature that you see to be lower here, actually, assuming that the convected air is at a lower temperature than the weld, which I think is a pretty reasonable assumption. Right? You would not expect to be welding at extremely high temperatures like that. So convection is the environment. What else do you think maybe a bit is here in this analysis? Radiation. So,
I guess that's not because it's not a laser, it's a plasma. So I guess that would
well, it's still though the surface is hotter than the environment, right? So you still have radiation. Okay, so radiation is basically heat loss via photon transfer. So anytime you have two different surfaces of different temperature, you have radiative heat transfer between those two different surfaces. What about this assumption about infinite? Basically, this plate is of infinite size, and the zeta direction. In this case, the zeta direction is along this weld here, where my cursor is. You see my cursor right now? You can? Okay, so the zeta direction is along this surface here. The y direction is perpendicular to that, and then z is here. So what if, in fact, they're assuming that this is an infinitely large plate. What do we expect to do? What type of influence would that have on our model predictions? Yes.
If the size of the welding area relative to the entire size of the surface you're welding on is, if the size of your weld is relatively small, that's a pretty valid assumption. You might have heat loss through the sides additionally if you're dealing with a very small surface area.
Okay. Yeah, I definitely agree. So if we look at, they're saying infinite plates. Okay. Yeah, so the influence of this is if the weld size to plate size small, okay, probably not a big deal, right? Okay, that's the basic argument they're using here, right? Is that they're saying that let's make this really simple on ourselves. Let's take a case where the bead that we're welding is very small compared to the entire plate. That is now an infinite plate. So now if we didn't have a case, say for instance, this example from this book here actually, this would be a case where your weld size is actually pretty large compared to the width here in this direction. And so, so if you have that case, there's not a lot of area for heat to flow, right? So we're saying that convection at the surface is not very large compared to conduction. Then we would have basically every amount of heat that goes into this weld has to then stay in the material, right? There's no way for the heat to be exhausted or sent out. So we would expect if we were to go to the these, we said that the temperature prediction that we're given, that we find, is higher than it would be in reality because both of these are heat loss mechanisms here. The infinite plate assumption assumes that this system can continually be heated in one location. It's always dissipated off to infinity, off to really far distances. And so if we do not have an infinite plate, if we're welding something that's pretty small, this could be a large amplifier. large amplifier of temperature, right? So imagine now that this is like even half the size. All the heat that goes into here really has to stay in that part. It's just going to get hotter and hotter the more you weld it, right? So that could be a continual worry. Any other? Yes?
Kind of the change in surface area, because as you increase or make your weld, you're going to be adding more surface area, especially with the flat weld.
Yes. So not only surface area, but volume too, right? Okay, so as exactly, as you put more of this weld in here, you're adding surface area. That oftentimes helps to amplify convection. So kind of as an example, your radiator in your car, they try and make your radiator car have the highest surface area as possible. That's why they put these little tiny fins, so you can improve convection. Right? So if you add surface area, you're going to have more surface for convection to happen. You're also going to have more volume as well. So when you look at, if we go to their equations here, I don't think I have a good example. You can find them in the paper. Oh, here we go. Basically, you could think of the volume as lumped into the denominator here. There's not an explicit term here that's volume. But the larger the volume is, the larger the name, it's going to change your equations as well. So they're neglecting the increase in surface area and volume as you continually add more material. Any other thoughts of what they're neglecting? So some other ones that I thought of while looking at this, there are some things that are, so for instance, that they're kind of really small, but could be interesting, I'm not sure, is that these electrodes have this covering material that then becomes a gas. And so basically the energy input into the transform of the solid into gas requires energy. So that's going to be energy sink for the system. And I haven't armed you with enough information yet to look at this, but also you have convection. I'll play this video here. This is this video how arc welding works that we went through on Thursday. Okay, so basically you get convection of a material that's forced by a temperature gradient, and this actually convection is an energy transfer mechanism as well. So neglecting. We'll get into that later on in the course. It's going to be called Marangoni flow. This will be important mode of heat transfer in these types of processes. You can see it better here. You can see how you essentially get fluid flowing uphill because of this temperature gradient involving it. So we'll talk about how that actually is a pretty effective method for heat transfer in welding or also in the measuring process as well. More detail for that. So that's the starting topic I wanted to talk about. Is there anything that you found interesting in the paper that you thought more discussion? Things that maybe you still have questions on that you were unclear of? All right, so that's it. Then we switch over to module 3 for the class. Okay. Okay, so module 3 is, I guess we have 2 students who have not had a class in heat before. What are your undergraduate degrees? Composite materials?
Yeah.
Okay.
My material science and engineering.
Material science and engineering? Okay. But no heat transfer. Thermodynamics?
Yeah.
Thermodynamics class? Okay. How about fluid mechanics? No, fluid mechanics? Okay. This lecture is assuming basically mechanical engineering or industrial engineering undergraduate. So it's going to be a lot of review for those who have taken heat transfer or aerospace degree. So I guess I'd recommend grabbing a textbook in both fluid mechanics and heat transfer. And then the citations that are in this this document here are the ones that Ohio State uses as undergraduate textbooks for this material. I'm going to try my best to arm you with all the basic knowledge needed for this, but I can't possibly cover an entire 2 courses with the material in this kind of introduction. So we'll introduce ideas from heat transfer, fluid mechanics as we need them, but I can't cover everything. So I recommend getting those textbooks just as a reference to help understand the material better. So module 3 is the basics of heat transfer, fluid mechanics, and additive manufacturing. So we're going to go through some. I mean, for those of you taking these classes, these ideas should be reviewed. But I think it's good to have a little bit of a refresher on these before we start to use them. And, even things that we were talking about in this paper, we haven't covered yet in this class. I hope they were familiar though from classes you've taken before. So basics of heat transfer. The main thing to understand here is that there are 3 basic forms of heat transfer. So this is ringing a bell for some of you. The one is conduction, right? So conduction is the idea that you can have heat transfer through a solid. Example of, it's the best idea. If you put like a piece of metal in a fire, and if you have your hand on that piece of metal long enough, you're going to have to drop the piece of metal, right? Because you have heat conduction through that piece of metal from the hot area, which is in the fire, to where your hand is. So you have basically a transfer of heat energy, which causes an increase in temperature, or a flow of energy from hot areas. So you have the conduction. You have where there's energy, Q double prime, this would be called heat flux, always goes in the direction of it goes in the negative of the direction of the temperature gradient. So T1 is greater than T2. We have heat transfer or flux in the direction of T1 is greater than T2. So it's conduction. We'll go through all these a little more carefully in a second. This is convection of basically heat transfer via fluid. You have hot areas, and you can remove heat from the surface by blowing some sort of fluid across this. This is going past it, that fluid then takes some of the energy and convects it to another region. You've seen this too when you walk outside and the wind is blowing, right? You have some sort of heat transfer in terms of convection from your body. And then the last one is radiation. So this would, I guess the best example here is the sun. That's how the sun heats the earth, right? So you have extremely hot surface of the sun. There is a relationship in terms of photon transport between the sun and the earth. Or you've seen this if you've been close to a light bulb before, felt the heat from a light bulb, right? That'd be a case of radiation, base heat transfer. Okay. So conduction. So transfer of energy from the more energetic to less energetic particles of a substance. And so this can be thought of in terms of vibration. So temperature is just the average amount of vibration that's in a, right? This can be applied to gas liquids as well. But if you have a region, T1, which is greater in temperature than T2, that means that your molecules inside your solid are actually moving faster than the molecules in this bottom area here. Right, and so you can have that heat transfer in terms of this flux from the hot surface to the cold surface. Right. Again, heat always goes from hot to cold, which is the direction of that. Okay, so conduction. So the easiest way to describe conduction often is in one dimensions. So this is pretty similar to what we're talking about with the partial differential equations module and also that paper from Rosenthal, looking at temperature flow in a rod. So if we have this rod and we have a temperature 1 on this side, temperature 2 on this side, and then we have a gradient, and that T1 is greater than T2, we're going to get this flux, or heat transfer rate, in this direction, right? So if we were to basically take this rod of material and then T1 is greater than T2, we were to put it in sort of insulator and just dissipate over time, this would eventually turn into where the temperature is the same everywhere. But at this point, T2 greater than T1, we get heat transfer in the direction of T. Okay. So we can describe this heat transfer by this equation. So these are the things that we've looked at kind of briefly before, not very carefully. We have something called the thermal conductivity of the material. So you've probably experienced this before. Like I said, the idea of if you put a metal into the fire and you have your hand on it, right? You would expect over time that you'd have to drop that metal rod because it's going to get really hot. But if you put a piece of wood in the fire, you can hold that piece for a long period of time. And that's because the thermal conductivity of metal is much, much higher than the thermal conductivity of wood. Right? So then your hand's not going to get hot with the wood. This heat transfer rate is given in watts. Here. And so then the relationship between the heat transfer rate is given by the thermal conductivity times area times then the change in temperature over space. So if we have a temperature gradient in dt dx, we can find the heat transfer rate for that region. Oftentimes we normalize heat transfer rate by the area that it's going across. And this is when we normalize that, we call this heat flux. Any questions on that? So, like I just discussed, this may be too small to see here. Let me zoom in. Okay, so like I mentioned that you may want to look at find the heat transfer book. This would be one I recommend. Incorpore de Witt, Introduction to Heat Transfer. I believe, those of you who went to Ohio State for undergrads, this is the book that they still use here. Yeah, okay. Maybe. Hey, do you know?
Sorry, what?
Is this the book that the MEs still use here in prepare?
It's been a while, I have to go back and check. I know I still have the book, so
Okay.
I have to go back and check if that's the exact book.
Back when I was in school here in 2004, I guess that's what we used. So this is, I imagine it's still the same book because pretty much every university in the country uses this book. It's very popular. So I'd recommend getting this book if you want some more background on heat transfer. But the,
Do we have this PowerPoint on Carmen?
sorry?
Do we have this PowerPoint on Carmen?
Yes.
Okay,
Yeah.
I don't have that on mine.
Sorry?
I don't have that on my Carmen page. Sorry.
Okay. I'm pretty sure this module should be loaded.
I have module 1, 2, 4, no 3.
Oh, 3? Okay, I may have made a mistake when uploading it then. Okay. I'll check that after class then and make sure it's uploaded. Okay, the main message here is that different materials have different thermal conductivities. So if you look at, say, copper, really, really high thermal conductivities. Stainless steel is getting lower. If you get down to things like quartz, pretty low thermal conductivities. The other thing to point out is that these are temperature varying terms, right? So we didn't go through all the things that this Rosenthal paper left out, but they assumed a constant thermal conductivity, right? And so we can see here that thermal conductivity is temperature varying. That's something that they assumed is constant. So that would definitely change the temperature profiles to some degree. So this is just a sampling of a bunch of different metals. If we were to look at metals that are going to be popular or important to additive manufacturing, some ones that you see all the time is stainless steel 316. So this is used oftentimes in the medical industries. They want stainless steels. Ti-64 is used in aerospace all the time. Inconel is a nickel-based superalloy that's used in aerospace as well all the time. And then these are less common, the steels, regular carbon steels, and also aluminums. But people have defined what the thermal conductivity of these materials are through really careful experiments, essentially. People have found out what the thermal conductivity of these are. This is in this paper that will be reviewed. Exactly when we're doing this paper, I believe it's the next one, which is Thursday. Which is this really long survey. So you can find this information and more in the survey here. The main thing to point out here is that they give the thermal conductivity here as a polynomial. This goes back to the idea that thermal conductivity is temperature varying. Okay. So this plot here, the top is just random set of materials. Here they're saying the polynomial for the thermal conductivity is given by these coefficients. Another thing to keep in mind is that these values here are thermal conductivities of a solid. Okay, so now you can imagine if you have powdered materials, which will have an additive manufacturing quite often, that the thermal conductivity into that powder is actually quite low compared to the thermal conductivity of the bulk. Okay, so if we look at what is conduction, conduction is heat transfer from basically more highly energetic particles to more lower energetic particles. And basically heat transfer is transferred via vibration of these particles. So now if you have a bunch of powder, and this powder is not, let's say, intimately connected to each other, you have a bunch of powder that's somewhat packed, but not really strongly packed, you have a lot of air in between, you actually have an effective thermal conductivity that's much worse than if you had a solid chunk of material for that. So papers like this is a additive manufacturing paper where they look at the effective conductivity of different materials here. What this is showing here, maybe tough to read, is this is basically the ratio of a powdered material versus the bulk, or the inverse of this ratio, as a function of filling factor. So about the highest you can pack a bunch of particles is about 75%. Usually if you just were to throw powder down on the ground, it's going to be somewhere in the 50% range. Okay, but you can see this is the ratio of those conductivities via the filling factor. So you can see a general, as you pack this powder more densely, you get a better conductivity. I'd have to look exactly at this ratio again, what that means. I'd have to look at the paper again, but there's a change. Does it make sense that the conductivity is, I have to look at these numbers. I wouldn't expect it like 20 times conductivity of the powder versus the bulk, something. So I have to figure out what that 20 means. But basically the effective filling factor influences the effective conductivity of the material. And we'll look at how that's important in terms of, does heat very appreciably transfer into the powder that's around a part we're making it or not. Okay, so we went through 1D conduction so far. Conduction is a 3-dimensional phenomenon, right? So heat conducts in all directions. So we have to consider how to handle that appropriately. So going from 1D to 2D, you can say, all right, that we have conduction in the x direction here, and conduction in the y direction, and also a resultant conduction normal to some sort of isotherm. So if we have some sort of surface, and we have an isotherm, which is basically a line or a plane at which the temperature is constant, and we know that heat always transfers across that gradient, then the heat transfer is going to be along the perpendicular to this isotherm, which is given by this vector n, right here. We can quantify the heat flux via this relationship. So if we say we have a constant thermal conductivity, we can break down this heat flux in terms of a derivative of that temperature with respect to the x direction, y direction, and z direction, and then I, j, k is your standard unit vectors along the x, y, and z directions, which you may have seen in solid mechanics, fluid mechanics, other courses like that where we use those vectors, unit vectors, x, y, and z unit vectors. So the reason why I bring this up is this can, depending on what papers you read, what other works you read, change how we represent boundary conditions sometimes. So before we were saying that at this insulated edge, we had the Newman boundary condition where we had that the partial of V with respect to x at this interface here at x is equal to L is equal to 0. Okay, an alternative way of saying this is that the Laplacian, remember again, this is dy d zeta dot product with n. If we say n is a unit vector going from this surface outward, should be equal to 0. So these are just two exactly the same ways to say the same thing. You'll see this actually a little bit more commonly in the literature, is this basic dot product with a unit vector denotation. Okay. So conduction. If we want to look at the diffusion equation, we can look at a unit cell. Here, I'll zoom in again. Okay, so I'm just going to go through basically heat transfer in the x direction here really quickly. But if we have a unit cell of dimension dx, dy, dz, we can look at basically the heat storage or heat transfer through this unit cell and just imagine that this unit cell is infinitesimal size, so an extremely small unit cell here. And so everything here is based on conservation of energy. In terms of the rate basis form of the conservation of energy. And so we're going to say for any unit cell that you have to have a balance of the heat rate of heat into that unit cell. So this is going to be essentially heat transferring through the boundaries of this unit cell plus heat generated. Okay, so En. En is basically heat going through the boundary in this direction. So we have a unit cell, heat is coming in, and this would be coming in. Say, for instance, looking at conduction, heat would be coming in because the cell to the left of this is hotter than this cell. Right? We have heat conduction. Generated would be that there's something in this cell that generates heat. Okay, so this could be a laser source causing the temperature in this region to be hotter. That's heat generation. It also could be chemical in some cases, right? So if you have a chemical reaction in the region, you can have basically resistors that generate heat inside of parts, right? So this could take on a variety of forms. This is the generated heat in the region. We have heat out. Okay, so that's what's going through the right side here, Qx plus Dx, and then that should be equal to the energy stored. So energy stored is in the form of basically an increase in temperature of that unit cell. And so just to note, this is going to form chemical, electrical, radiative, a lot of different fault sources generated heat. All right, so looking at En, okay, so En, if we look at this little unit cell here, we have coming in, we have heat, or Qx, we have Qy, and we have Qz all coming in to this unit cell here. All right, coming out, okay, so in the x direction, what we have here is, in the q out direction, we have q at x plus dx. This is the heat at this surface, and we can say this is equal to this heat going through plus the change in heat going out over this per unit length times then that length, dx. Right? So for that, I'm just going to follow in the y and z directions, just follow directly from there. Okay, energy generated, this is kind of the generic term, but this is equal to Q dot. This is in watts per meters cubed. Okay, so what this is saying is that we have some sort of heat generated inside here, and this is in terms of watts per meters cubed. So therefore, if we want to know how much heat generated in a small, infinitesimally large block, it's watts per meters cubed times dx, dy, dz. To understand how much heat is generated in a unit cell. And then lastly, energy stored. Okay, so energy stored is given by its density. It's always going to be in units, kilograms, meters to the negative third. It's going to be given by a specific heat. Okay, so specific heat, what this tells us, this is the ability of a material to store energy. So an example, water has a really, really high specific heat. That's why it's often used in heat convection methods, like in the radiator car, or the materials very close to water have really high specific heats. And so what this says is that we can, in terms of the amount of energy that can be stored, so this is in joules per kilogram per change in temperature. This is specific heat. So water is a very good way to store energy. Metal is not as much, but water has a very high specific heat. This energy storage is proportional to the amount of energy or amount of temperature change per unit time. And then this is the volume of the material, this infinitesimal little block material, right? So if we look at units here, we have kilograms, meters to the negative third. This is going to give us meters to positive third, right? So meters to the negative third cancel out. This is in joules, kilograms per Kelvin. Joules per kilogram per Kelvin, so this kilograms canceled out. And then we have change in temperature over time. This is going to be then Kelvin per second. I cancel out Kelvin, so what we get for energy storage and every other term here, we get joules per second, which is also equal to watt in terms of units of this. Okay. All right, so we have this equation, we have all these subparts of this equation here. The other thing to keep in mind here is that if we look at this Qx, okay, so this is, if we look at the linear relationships we're looking at, Qx, this is basically heat transfer rate is negative, right? Because heat always transfers in the negative direction of the gradient of temperature. Then it's times area times then dT dx. So the area in this case, though, is going to be, if we look at in the x direction, right? The area which this is transferring through is dy dz. If we look at the area of this. Right? So this becomes dy dz. So why that helps us is because before we had these terms here, say qx, sorry, this one right here was, because these are going to, this qx and say this qx cancel out, this is qy here. We had dx, or sorry, we had this, there's a change in qx via x, right? This way the dx here, by adding them, it's dy dz, and this having dy dz, this having dy dz, those are all going to cancel out for all of our sub-equations. So what we can do is that we can put this all together. This long equation becomes conservation of energy equation. So in a second, I think you'll see how this is very similar to the 1D diffusion equations we were looking at before. What this is saying, I'll show you how to simplify this in a second, but if we already said that thermal conductivity is not constant temperature, right? So this changes or material as we change temperature. So this is never going to be truly constant. Sometimes we can assume it's constant to make our life easier. Right? So this k is no longer a function of x. That allows us to basically pull k out, and that makes this a much more simple expression, because then we get k squared t dx squared. Y direction is the direction. And storage time. Okay, so how you'll most frequently see this in journal articles is probably in shorthand here, which you have the Laplacian. Squared t, this is from the notes for three-dimensional partial differential equations. We have Laplacian squared t. Divided by k. And then we're going to have that 1 over what's called a term called the diffusivity of the material. Okay, so this is diffusivity is a material property. It's a well-known material property. So this is the thermal conductivity of the material divided by its density. So I'm going to show its density and its specific heat. So this is a material property that is in a lot of additive manufacturing literature. It's in heat transfer books. It's in a lot of sources which use it. If I have a certain material that I'm looking at heat transfer through, you can find this information basically for all of these terms. This has been well cataloged by engineers and scientists many, many years ago. Any questions about conduction? So many of the early models that we're going to look at, we're going to look at only conduction. Just like the Rosenthal paper, we'll look at only conduction because that's a good starting space. We'll look at it and we'll talk about why conduction is going to be one of the dominant heat transfer mechanisms. Okay. Let's take a 5-minute break and reconvene at 10:55, and then we'll get into some of the other modes of heat transfer. Hey.
Quick question, so for the problem figure the homework, you didn't supply any values for K and L, and you want us to animate, should we just declare them?
Yeah,
So-
just declare them as one, essentially. So yeah, it should be here, module 3. Yeah, let me know. Can you? Is this the? You usually use your tablet, or do you use a desktop computer? What do you usually use?
Actually, in that block, see that gray line there?
Oh, that's the issue. Okay. I accidentally turned that off. Okay. There you go. Now it should work. Sorry, I can see it, but you can't. Thanks. Make sure everyone else is. that was conduction, which in a heat transfer class would take you probably 5 or 6 weeks, maybe longer. We don't have time to do that, so that was really the basics of conduction. Another module that would usually take you 5 to 6 weeks in a heat transfer class would be the idea of convection. And this is going to be extremely brief because, frankly, convection is one of the more difficult heat transfer modes to analyze. So it's such a varied field. It's very dependent on geometry. It's dependent on a lot of things. So when we have specific cases of convection, we'll talk about the equations for that specific case. But where you see convection, and what's kind of like always the introduction to the idea of convection, usually fluid flow over a flat plate. So those who take a heat transfer class, this is probably some of the first problems you ever dealt with convection. But the main idea of heat or convection is heat transfer modes. It's comprised of 2 different mechanisms. You see one is random molecular motions. This is diffusion. So if you have, it's called, oftentimes you'll hear Brownian motion, but basically you have a fluid and all your molecules are randomly moving around. And the process of taking a molecule, which has a certain heat, built up in it and moving it to a different location, that is a process of convection. You're moving heat from one area to the other. Also, you have what's called advection, which is bulk motion of a fluid. Okay. So if you have a hot surface, so imagine a surface of your stove at home or something like that, and then you have a fluid flowing over top of that. Heat is transferred through to that fluid, and that fluid is then pushed downstream. Right? So you have a net heat transfer because you have heated air, which is taking heat from that surface and moving it to a different location. Right? So you have energy transfer via just bulk flow of this fluid. It's important to know that there are basically 4 different types of convection. So one is called forced. So I'll zoom in here so you can see this a little better. One is called forced. So you see that actually a really good example of forced convection is what's going on in this air conditioner right here. So you can hear a few things happening. One is that you may notice that there's air blowing out this. And so that is forced convection. There's a fan inside there that is forcing air basically from the inside. It's going through the system, and then it's forcing air to go through a heat exchanger, and it's basically causing, in this case, cooling the air, but you can also think of cooling as just the opposite of heating the air. Okay, so we have air going through this heat exchanger, which is made up of a bunch of fins, and that is then transferring heat via that mechanism. You see this in the radiator of your car. You've seen this if you ever put your hand in front of a really high velocity fluid, you notice that it is cooling your hand. But this would be an example of forced convection. The other one is natural convection. So this is flow induced by either buoyancy forces or surface tension gradients. So you'll see natural convection in terms of multi-pane glass. You actually have air flowing between the multi-pane glass because you have a hot section which causes the density of the air to decrease. The cool section is causing the density of the air to increase. And because of basically a gradient in the density of your air, you get this circulation, which is also a heat transfer mechanism. So this would be, for example, natural convection. In the book, they're showing natural convection of heated circuit board elements. Again, same idea. You get heating of air in one location, which causes a decrease in density. The colder air is in a higher density. You're going to have now circulation because of this. And the other 2 are boiling and condensation. So you've probably seen these before. This is what's called latent heat transfer. So it's the idea that there is a certain amount of heat that's stored in a transition of states. So anytime you have a transition of states from liquid to solid, you have a certain amount of heat you have to overcome, and you can also transfer heat by that as well. But you see this in boiling, and you also see this in condensation. So this is the mechanism of why we sweat. So the fact that we can turn liquid on our surface of our skin into a gas, that's a very, very efficient heat transfer mechanism, which is why we sweat, and then that causes us to cool down. These are the 4 basic modes of convection. I believe that's actually all I have to say on this. because it's such a complicated subject. So we'll introduce ideas as we need them for that one. Radiation. This is, like I said, how the sun heats us, but this is anytime you have a surface that's at some sort of surrounding temperature, and you have another surface which is at a different temperature, so you have a temperature gradient between the two. You have heat transfer basically by the transport by electromagnetic waves or photons. So this is how the sun heats the earth. This is how you feel heat when you have a light bulb that's shining on you, etc. That's how you can probably answer the magnifying glass, right? That's the heat transfer via radiation. The important thing to keep in mind is this is a product of many terms, and this is always temperature to the fourth. Okay, so this is why the sun is such a very effective radiative heat transfer mechanism. The sun is extremely hot, and you take that to the fourth, that becomes a large amplifier in the amount of heat you can transfer via radiation. It's also a function of something called the emissivity of a material. And so emissivity is a material property. And this is an example of, this is a pretty old paper. This is looking at the emissivity of a few different materials that which we would use in the heat treatment and or additive manufacturing. It's important to note that these are, it's a product of many different things. The one thing I want to point out in this graph here is one is the function of temperature. So as you get hotter, emissivity increases. That means you have a more effective heat transfer mechanism. So emissivity is always between 0 and 1. It's unitless. Basically, the heat transfer rate as the surface gets hotter improves. And the other thing to point out is it's actually very much dependent on the surface quality of what you're making. Okay, so if you look at these different surface conditions for the different metals, this is basically just ways in which they treated the surface. You get different emissivities depending on this surface characteristics. Right, so these are exactly the same materials, different oxidations, and also different surface treatments, different emissivity. So it's going to be a very, if you look at the additive manufacturing literature, no one really has come up with a really great way to characterize this emissivity for additive manufacturing yet, actually. It's known that it's a fairly important heat transfer mechanism, but it's not very well understood. And so why this is difficult is that the surfaces you get with additive manufacturing are still very rough. And the surface roughness directly affects heat transfer via radiation in additive manufacturing. So no one quite has figured this out. They're actually using a lot of fudge factors to do this right now. Okay. So that was that was a crash course in heat transfer, now into fluid mechanics. Same basic idea that we're looking at. Everything for fluid mechanics is built off of this idea that we have some sort of unit volume of fluid. And we can now characterize this. Before we talked about the amount of heat in the fluid, oftentimes we're talking about fluid mechanics, we're talking about the velocity of the fluid going through this unit volume. Okay, so we're going to denote some sort of unit volume, and then the velocity field in that unit volume is u in the I direction, or that's in the unit vector. It's the unit vector in the x direction, v in the y direction, and w in the k direction. This is the main way in which we describe a velocity field. So know that this velocity is a vector, right? So it's not a speed. Speed is always positive, and it's just basically if my car's going 60 miles per hour, I don't denote that 60 miles per hour to the north, right? I just say 60 miles per hour, that's my speed. The velocity field is always a vector, and that has velocity in the x, y, and z direction. Okay, so any control volume, this is just a control volume in space, must satisfy continuity. I don't know why I can't use my markers right now, but oh well. So must basically satisfy continuity. That means that the time rate of change of mass is equal to time rate of change sorry, I have a typo here. I copied this twice. Time rate of change of mass, the control volume to the net okay, sorry, the time rate of change of mass is equal to the time rate of change of mass and control volume to net rate of flow of mass across the control surface. So sorry, that's not very clearly worded. I'll work on that. Has to satisfy Newton's second law. This is essentially momentum equations, and it has to satisfy the first law of thermodynamics. So we're not going to talk about this all that much for the basics of fluid mechanics. But going into this idea of continuity, same idea as before. We're looking at unit cells. The other image for heat transfer is looking at in X, Y, and Z. But if we just look at the X direction here, we can say that we have some sort of mass, right? So mass times the velocity is essentially the idea of momentum, right? So if you look at the density of this fluid times its velocity, and then we're subtracting out any change in the momentum of this fluid going in the X direction. On the right side, sorry, it's cut off a little bit, it's just the opposite. This density times U plus then any net change. So you have the left side and right side of this. You add these together, and then if you combine these in all directions, you get this equation here. Basically, change in density with time. Oftentimes, we're going to be talking about incompressible fluids here, so the change in density is going to be equal to 0 with time. So we're not going to talk about, when you have compressible fluids, you get basically compaction of the fluid, the density increases or decreases. Here we're going to oftentimes call this change in density with time is equal to 0. And then we have our relationships for fluid flow through this control line. So this is d rho, d dx of rho times u, which in vector form would just be this equation. We'll get into simpler forms of how we're going to use this later, but this is the basic form for any control volume. Newton's second law. Okay, so Newton's second law, we have to look at then all the forces that are on a certain control volume. So for those of you who have taken solid mechanics, etc., you should be very familiar with the ideas of normal stress and shear stress, which are given right here. But this unit volume has a stress in the x direction, given by here and here. So this is the amount of stress. This is also the change in stress in the direction of x on both the left and the right side. We also have shear stresses at the top and bottom surfaces, and at this side and this side here. So this would be expressions in terms of how we determine what is the stress on this unit volume of material. So we can add these up in the x direction, and then we know that this has to be equal to then basically F is equal to ma. Right? So we have then change in velocity per time, and then also change of velocity in all the different directions. So all your forces on this unit volume have to equal then your mass, or effectively density, or basically change in velocity. Right? So this is just Newton's law, F is equal to ma for a unit volume material, and then we can do this in the x, y, and z direction. I forgot to note, this is the force from gravity on your material. Right? So if you have a unit volume of material, it's going to have some sort of gravity on it. Sometimes we'll care about this, sometimes we'll ignore this, because it can be pretty small sometimes. In this class, we're always going to be working with viscous flows, and so viscous flows, this never simplifies the Bernoulli equation, which you may have seen in your undergraduate class. I probably did that very often in fluid mechanics, but we won't really have that case. We're going to look at fairly viscous fluids in this class. So this never simplifies the Bernoulli equation, but we will look at fluid flows that are very viscous, and to do this, we have to get into some concepts in terms of viscosity of materials. So you may have, if you've never taken a fluid mechanics class, you probably have heard of viscosity in terms of you have a very high viscosity material, low viscosity material. You may understand what that means in terms of, say, something like syrup being very high viscosity. Something that is lower viscosity would be water, right? But there are formal ways to look at the viscosity of certain materials. So the viscosity is basically the relationship between the shear stress on a fluid to its velocity profile or shear rate. Okay, so the shear rate would be the change in this, and if just looking at 1D, this would be the change in velocity in the u direction with respect to the normal direction, right? So the shear rate would be the slope of this line here, and then the shear stress would be the stress on this unit volume material. So this can be measured if we look at putting a force sensor on this plate that's moving with velocity u. We can determine what is the relationship for material between shear rate and shear stress, and this is this viscosity or longer form dynamic viscosity here, mu. And so this is for what's called a Newtonian fluid. So water would be an example of Newtonian fluid or approximately Newtonian fluid, but there's also going to be a lot of materials we're going to look at that are not Newtonian fluids. So a Newtonian fluid has a more complex relationship. So the shear rate is a nonlinear function of, the shear stress is a nonlinear function of the shear rate. And so looking at this plot a little bit more carefully, this is what's called a Newtonian fluid. Again, so linear relationship between shear rate and shear stress. A non-Newtonian fluid or any other of these other profiles on this plot. Okay, so we no longer have this linear relationship. So some materials are called pseudoplastic. And so pseudoplastic means somewhat like plastic materials. And so the idea is that there's a nonlinear relationship, that this shear stress is a function of some constant times then an exponent on the shear rate here. So if this material is what's called shear thinning or pseudoplastic, that means its n is less than 1. So what that means is that as the shear rate increases, the viscosity is essentially the slope of this line. As the shear rate increases, the viscosity decreases. This is very common for a lot of polymer materials. So if we look at the slope in this region right here, it's quite high, and as the shear rate increases, it decreases. Are called shear thinning. We won't really deal with dilatant materials. This is often considered to be a very bad material property. You would never use this for additive manufacturing, because what this means is that as you shear it, it becomes more viscous. There's some materials that behave like that, but they're not really useful for additive manufacturing processes. A more complicated fluid is called a yield pseudoplastic fluid, and what this means is that this has a non-zero yield stress. Okay, so what this means from a materials perspective is these are materials that hold their shape when they don't have a shear stress applied to them. So toothpaste is an example of a yield pseudoplastic fluid. So you squirt your toothpaste on your brush, it then holds its three-dimensional shape. It doesn't just flow into your brush like water. Right? But as soon as you start to shear it or put some sort of stress on it, it becomes actually a very low viscosity and it spreads quite well. Right? But a lot of materials for additive manufacturing are actually yield pseudoplastic fluids. So just to kind of point that out, here are some. This is from this is not from any. This is from a book, and this is looking at the rheology of rheology, or basically the study. Rheology is the study of viscosity of some materials that would be used for additive manufacturing. So if you look at the MakerBot type tools, they look at basically the melting and then resolidification. But when it's melted, you have to flow it. The melting of, say, nylon or polypropylene are two materials that are used in additive manufacturing, and then they can give you the N, which is called the fluid behavior index, and M, the fluid consistency index for these type of materials. So this kind of gives us ranges of what you would expect for this viscoelastic or viscosity parameters for these materials. Okay. If we assume that we have Newtonian fluids, which is we'll have to start for a lot of these processes, we can start to simplify all the equations in terms of the continuity and satisfaction of Newton's laws to a more simple relationship, which you've probably heard of, called the Navier-Stokes equations. Right? So if we have the relationships between shear stress and shear rates, our Newton's equations now become what's called Navier-Stokes equations. Those of you who've taken fluid mechanics, you probably hated these, but they're very important to try and understand fluid mechanics. These are famously difficult to solve nonlinear partial differential equations, which we'll be looking at some very, very simple cases. It's nothing like what you'd see in a graduate level fluid mechanics course. But these are the nonlinear Stokes equations, and these can often be expressed in vector form here. So we'll look at just a few simple cases of these, which is the nonlinear Stokes. Okay. The last thing I wanted to talk about, and this actually segues quite nicely into the next lecture topic, which is going to be non-dimensional numbers for additive manufacturing, is the idea that there are different domains for fluid mechanics. So, and those who take fluid mechanics, that's probably heard of laminar flow and turbulent flow. Those of you who have not, you probably have heard of turbulence in terms of the last time you were in an airplane, maybe. The laminar flow, this directly comes from the word in Latin called lamina, which means thin sheets. Okay, so you can think of laminar flow as all the molecules in a certain region acting like a single sheet, and that sheet is flowing past all the molecules in a different region in a fluid flow. So this would be a case in a pipe. This would be you have lamina or sheets of cylinders of molecules which all have the same velocity, and those have a different velocity than ones that are radially farther away from the center of this material. So laminar flow, you'll see that you have streamlines of fluid, and these streamlines of fluids will stay constant through the length of some sort of tube that's flowing through. And that means that basically you do not see, besides diffusion, molecules going farther away or closer to the very center of this tube. Transitional, I'll skip that in a second and talk about turbulent. Turbulent means that there is that the inertial forces in the fluid in this pipe are much higher than the viscous forces, and so there's a lot of randomness in where the molecules go in a flow in a turbulent flow. Okay, so that if you were to put a dye into a turbulent flow, you would see then this dye is just going everywhere. And then transitional is then the space in between. In terms of it's not fully laminar, it's not fully turbulent, it would be transitional flow. And so the way in which we describe, this would be the case of the pipes, to decide whether or not a fluid is laminar or transitional or turbulent is by looking at something called the Reynolds number. So the Reynolds number is the ratio of, of inertial forces to viscous forces in the flow. So inertial forces are basically ones that are related to velocity of the material. Viscous forces are ones that are related to the viscosity of the material. And this Reynolds number is given by this equation here. We've already defined density and viscosity before, so I'm not showing this, but then we have average pipe velocity and pipe diameter. And then we have regions where if the Reynolds number in a pipe is below 2100, it's called laminar. And so we'd expect a flow profile that looks like up top. It's greater than 4000, we call it turbulent, which would be this behavior. And if it's somewhere in between, we call it transitional flow. So depending on what we're looking at, oftentimes, if we're looking at fluid flow through a pipe, we're talking about extrusion of materials, and these materials are often of very high viscosity. It's going to be laminar flow. If we're looking at airflow and some of the additive manufacturing processes across plates, which is what's next, it may be of considerably higher Reynolds numbers. It's oftentimes laminar as well. So we're going to mostly be looking at laminar flows. We can also look at laminar flow across the plate. And so this is fluid flow across the plate. If you have a fluid going, it hits the edge of a plate, you have this development where it will eventually change from laminar to turbulent, but this is dependent on this position X. So it'll be laminar closer to the front edge of the plate, turbulent closer to the back edge, and we can determine this Reynolds number as a function of distance along this plate. And so note that this laminar to turbulent transition here is very geometry dependent. So this is 10 to the 7 for flat plates. Before we were talking about somewhere around 10 to the third. So considerably different ranges for laminar versus turbulent flow on flat plates versus in pipes, etc. But you can see a fairly similar description for Reynolds number across the flat. Okay. So that was a crash course of 2 different undergraduate courses in like an hour. So necessary, but I hope that was a little bit of a refresher for some of those who haven't seen this material in a while, kind of getting you up to speed on the language that we'll be using. All the details we'll cover it in detail when we get to certain processes that need that. Any questions on this material? Besides a lot of questions. Okay, we'll start to use some of these. This is the end of this module. We'll start to use these Thursday. Okay, I see you then.